to be part of this wonderful event. It's always been a great honor and pleasure coming to Satyabama University, not only because we have two high-end instruments, a TM and an XPS here, but also the friendliness and the warmth the faculty members extend to ThermoFisher here. So it's always been a pleasure for us to keep visiting Satyabama University. And particularly looking at the agenda of this workshop, it's a sense of satisfaction that we are being a part of an event that not only gives exercises students on getting hands-on demo with the instrument. So that's a whole package that has been put around this program schedule. So my name is Karthick Balasubramanim. I work as a senior product manager in the electron microscopy division of ThermoFisher Scientific. So when we say the electron microscope division, it includes a scanning electron microscope, transmission electron microscope, dual beams, and also XPS. So we serve the entire range of electron microscopy and surface analysis solutions. And I support our sales team both in terms of technical as well as the commercial support. So that's a quick introduction about me. So ladies and gentlemen, over the next 40 to 45 minutes, we are going to discuss about a technique called XPS, X-ray Photoelectron Spectroscopy. So if you look into the literature, XPS is also referred as ESCA, Electron Spectroscopy for Chemical Analysis. This technique has been in existence for more than 40 to 45 years. But ever since the nanotechnology zoom came up in the early 2000s, the importance of surface analysis has gone to unprecedented levels. Whatever might be the sample that you are working in, or you might be working in any kind of a research area, unless you characterize your samples with an XPS, your analytical characterization remains incomplete. So that's the importance XPS plays with the modern age of materials, particularly with the improvement what we have seen with these advanced and functional materials. What lies on the top surface plays a very, very important. The composition and chemistry of the top surface plays an absolutely important role in your understanding of the material. And in order to derive the composition from the top surface, X-ray photoelectron spectroscopy is the only instrument which can get you the data. So over the next few minutes, please do stay with me. We will look around some of the basics of XPS. Most of you might know it. I'm not denying it. Most of you might know it. So the basic slides, what I will cover, it is particularly aimed at the student community who want to get to know more and more about this fascinating technique. Before I get into talking about the technical details, we belong to ThermoFisher Scientific, and ThermoFisher Scientific has been the world leader in serving science. Our mission statement is to make the world healthier, cleaner, and safer. And we make equipments which helps our customers to drive towards this mission. And ThermoFisher Scientific, we have branch offices all over India, and there are more than 1,000 colleagues who are on the customer facing field, facing customers. Now let us talk about XPS. Advancement of this modern age of materials. It could be whatever. You might be working in the field of petrochemicals. You can be working in the field of thin films, semiconductors, carbon-related materials, or glass industries. Whatever might be your research area, or whatever might be the sample that you are working on, understanding the surface becomes absolutely essential in the modern age of characterization. Why you want to characterize the surface? Because the surface is the point where it interacts with the external medium, or it interacts with another set of samples. And You want to understand what is the composition or the chemistry on the top surface, because the surface defines the property of the material. Either it can be the conductivity property or the porosity or even the material. They lie all on the surface. So if you overall understanding of your material, characterization of the surface becomes absolutely essential. And that's where X-ray photoelectron spectroscopy plays a very important role. And if you'd followed me in the last 5 minutes, you would have seen that I keep repeating the term surface again and again. And I'll be repeating it again as well. So what does a surface mean? Why do I keep repeating that surface? Any sample that you take, either it can be a metallic bulk metal, or it can be a powder, or it can be a fiber. Any sample that you take, your sample can be divided into certain regions depending upon the depth thickness. On this schematic, the top layer that you see, which is marked in red, that corresponds to 1 nanometer, roughly 3 atomic layers. And in true sense, we call this as a surface. And the next layer, what it comes marked in blue, they correspond to about 1 to 10 nanometers, roughly 30 atomic layers. So whenever you do any characterization on XPS, any data that you collect comes from the top 2 layers of your sample, which is 10 nanometers, roughly 30 atomic layers. And this is what we call it as a surface analysis when it's come to characterization. The layer below this surface, which is marked in green, is often called as a thin film, and these layers are called as the bulk. Now, in terms of depth of characterization, what is the difference between XPS and other techniques? We just saw that the XPS gives you information from the top 10 nanometers, whereas on the other hand, every other characterization technique that you use in the lab, either it can be XRD, it can be XRF, or it can be an EDS attached with an SEM. These all techniques help you to understand the composition. All these techniques give you information from the bulk of your sample, which is about few tens to few hundreds of microns. So if you want to get an overall understanding of your sample, both on the surface as well as the bulk, characterizing using all those techniques, XRD, XRF and EDS, and also characterizing using XPS, the top 10 nanometers, that gives you an overall understanding of the sample. And particularly with the modern age of materials, what you find, the surface plays a very, very important, and you cannot avoid characterizing the surface using XPS. And that shows the importance of an XPS. Now for the next 5 minutes, let us take a quick history into what is the theory behind XPS, X-ray photoelectron spectroscopy. So XPS was a technique which was first discovered by Einstein, as most of us know. He was the first one who brought out the concept of a photoelectric effect. What he mentioned is that when you shine on a surface of a sample using any source of known wavelength, you get photons which come out of the sample surface. So that was a theory he mentioned as a photoelectric effect. That was a great discovery, but until someone took the technique and built up an useful instrument out of that technique. So after Einstein discovered this photoelectric effect in 1960, we had a Swedish scientist called Dr. Seibach. So Dr. Seibach found this photoelectric effect theory to be greatly applicable in many areas of science, and he discovered an instrument which he named as ESCA, electron spectroscopy for chemical analysis. So his discovery at that time helped us to barely understand the composition from few hundreds of nanometers, and this technique gradually grew up, and once people understood the importance of it, Seibach got awarded with the Nobel Prize. So basically the takeaway message is that XPS works on the principles of photoelectric effect. So now let us take a bit of a deep dive. It might sound sort of a school science what we are looking at. So what happens in an XPS is quite interesting. We all know that a material constitutes of atoms. And when we look down at the atom, you have a nuclei in the center. And you have electrons which are revolving at certain fixed orbitals. The number of electrons depends upon the atomic number of an element. Now on an XPS, what we do is that we take an X-ray. We take an X-ray of a known energy. We take an X-ray of a known energy and we shine it on the surface of the sample. So as these X-rays pass through your sample, they come in contact with the electrons which are in the orbitals. Now these X-rays, with their energy and momentum, they impart their energy on these electrons, and that is quite sufficient to knock this electron out of this orbit. And this electron, which is knocked out, is called photoelectron. Now it gets interesting. On an XPS, what we do is we collect all these photoelectrons that come out of the sample, and we collect those photoelectrons and we measure the kinetic energy with which these photoelectrons. Now, one question that might come to us is that why do we need to collect these electrons and measure the kinetic energy? That's where the mathematics gets interesting. Now you are collecting the photoelectrons and measuring the kinetic energy. You know the energy of the X-ray which you are using as a source, and combined with the work function of the instrument, in turn you calculate the binding energy of this photoelectron. Again, why calculating binding energy becomes so important is that when you know the binding energy of a photoelectron, it tells you from which element this photoelectron got ejected and from which orbital it got ejected, and more importantly, when it got ejected, what was the chemical state of the element. All these three information coming in a single measurement, that too from the top few nanometers of a sample, that's what makes XPS a very, very informative technique. Now on an XPS, there are a couple of experiments that we usually do. So XPS can help you to detect any element in as long as it is at 0.005 atomic weight percent. So that level of sensitivity it can deliver, and it can deliver every single element on the periodic table with the exception of hydrogen on the hydrogen element. But now there are certain techniques which can indirectly also calculate the amount of hydrogen that is present. So when it comes to an XPS, usually there are two kinds of measurements every user will do for every sample. The first measurement is called as a survey scan. The survey scan helps you to scan across your sample over a wider energy range. So when you scan across a wider energy range, you get to know every single element that is present on the surface of the sample. And depending upon the number of counts you get for a particular element, the intensity of the curve goes high or drops down. So that gives us a fair idea what is present, and it is also a quantified technique. It tells you how much weight percent it is present. So this is first sort of a measurement that we do. And after you have done the first measurement, there would be certain regions or elements which is of a key interest to you. So you select a narrow region which is also called as a high resolution scan. And when you do a high resolution scan for a smaller region, and that's where you get the different chemical states present on your sample. For example, on this slide, there are two kinds of a polymer which is very similar, the spin cast polyethylene terephthalate, and you also have the sheet polyethylene terephthalate. Both are pretty much similar polymers, but they vary on the chemistry. So if you want to understand the difference in chemistry, then you do a high resolution scan of both these elements. That's how sensitive and accurate is an XPS technique, where it can bring out the mild differences in the chemistry between two similar elements. Now stepping forward, what makes this XPS so beautiful and interesting is that even for a similar element, same element, for example, on this slide, you have an iron. Iron can exist as a pure iron metal, or it can be as a ferrite oxide, or it can also be as an Fe2O3. So these are the different chemical states of iron. XPS is the only technique which can help you to identify the different chemical states of this element with a single measurement. And that's what makes XPS the most sought out technique for surface analysis. Now stepping forward, there is a question that comes to us is that, am I able to handle every kind of a sample? For example, I do have a conductive sample, or I might have a non-conductive sample. Am I able to analyze both of them? When you look into the olden day of XPS instruments, their charge neutralization or ability to handle non-conductive samples was very poor. So recording useful spectra with the olden day instruments was very, very difficult. But with the modern day instruments, you have a very good charge neutralization, which comes as a standard, and you can record spectra irrespective whether the sample is conductive or non-conductive. Now, as we step forward, one question that comes for a central instrumentation facility. For example, there are many CAFs around the country. One question that comes to us as a student is that, when I characterize my sample using multiple other techniques like XRF, FTIR, Raman, XRD, do I still need to do XPS? Is XPS a better technique than all other these techniques? The answer is yes, XPS measurement is very important, and there is no question which is better or which is less better. All these techniques are complement to each other. These techniques give you very useful information from the bulk of your sample, whereas an XPS complements this information by giving information out of the surface of your sample. And when it gets more particular to surface analysis, if you look into the demands of the modern day surface analysis, and if you plot the requirements against the various techniques that are available in the lab, you will find all these techniques are complementary. But XPS is the only technique which can fulfill a very important role. XPS characterization can give you a wealth of information. So let us quickly summarize what we have seen thus far. XPS is a technique that gets you information from the surface. It works on the photoelectric effect, and on an XPS, what we do is we shine the surface with an X-ray of known energy, and this causes the photoelectrons to be ejected. We capture the photoelectrons and we measure the kinetic energy. In turn, using the kinetic energy and the X-ray, we calculate the binding energy of the photoelectron. A binding energy tells you about from which element it came, from which orbital it came, and what was the chemical state of the photoelectron. And when it comes to XPS, there are two kinds of a scan which is usually done for every sample. One is called a white scan that tells you what all elements that are present on your sample. It also gives you a quantification of how much it is present. And the second set of a scan is called as an high resolution scan, where you understand the minute chemical states of your sample that you are working on. So now as we step forward to the second leg of this presentation, we are going to have a demo on instrument K for model that is installed at Satyabama University. So this K alpha instrument, this has been a sort of a blockbuster when it got introduced in XPS around the year 2016 and 17, because this instrument completely changed the way how an XPS can be operated and the data can be collected. So this K alpha instrument can handle all of these samples. It can handle samples which are not even mentioned there. The only requirement when it comes to an XPS is that XPS works in ultra high vacuum, typically in the range of 10 to the power minus 9 to minus 10 millibar. So when you work with ultra high vacuum, it goes without saying that your samples should not have a water or a moisture content, or your sample should not degas the moment you put it under a vacuum. So these are the two requirements of an XPS in terms of sample handling. So this is the model that our colleague Suresh is going to show us a demo today afternoon and tomorrow. And this K alpha instrument can help us to do point analysis, imaging, and depth profile. These are some of the basic requirements of users who come for XPS analysis. A quick view, what are some of the important components which you will be looking through the demo is that this instrument is so compact. The reason why slide is that if any of senior users have used XPS in the past, or if you have visited to a surface analysis lab, days when I did my research, when I used to go for a surface analysis experiment, the used to be as big as this hall, from this end to this end, one single instrument. And it used to have multiple operators taking care of a single instrument. It was such complicated. And to get one data, you have to wait for weeks or sometimes even 10 to 15 days. That was the complication which was involved with XPS instrumentation. But this K alpha, when it was launched in 2016, it completely changed the dynamics of instrumentation. It brought automation into picture, and it made XPS analysis for every single user easy and affordable. And when you look into some of the main components, this is how your XPS K alpha looks like. And you will load your sample here, and from the load log, your sample gets transferred to the analysis chamber, and you do all the analysis in the chamber there. Now, one other interesting topic here is that the easiness of sample loading. So here you will see the operator is opening up the load lock and in the mass loader with multiple samples. Is that in instruments which were about 10 to 15 years before, sample loading on an XPS was multiple samples. You have to go with 2 or 3 maximum number of samples. You have to insert your sample, wait for the base vacuum to build up, and you have to push the magnetic handle very carefully into the analysis chamber. While transferring it, if your hand shakes a bit, then there is a vacuum loss and you have to wait for a couple of days for the vacuum to recover. All those nightmares have been taken care of, and it is as easy as loading the sample which is shown in this slide. And whenever we talk about an XPS, I mentioned that it works at ultra high vacuum. So when you go measurement, samples, as a user, you should have the discipline and the practice to take samples which have no moisture or water content. It is also your responsibility that when you take your samples, you should ensure they do not degas the moment you put under a vacuum. So these 2 precautions, as a user, you should take it. And this is a quick view of vacuum setup on a K-alpha system. It shows that it is a complete oil-free pumping system and it is completely automated. The transfer from one point to a higher level of vacuum, the vacuum management is taken care automatically by the software, and the user don't need to go and change the interlocks from time to time. That's been how easy in terms of instrumentation that has come up. Talking about the capabilities of an instrument to a great extent. And as a student or as a researcher, it also becomes very important to understand the instrumentation part of an equipment. Because we go for sample analysis, we get data, but we also understand the equipment or the instrument more and more. The more you understand, it helps you to drive the instrument to the fullest capability. With XPS, what are some of the important components, not only of K-alpha, but any other XPS instrument that you go across? These are some of the important components that you will find in every single XPS instrument. And when you understand what is the functionality of each component, that helps to calculate your understanding when you run an experiment. So it looks to be a complicated schematic diagram. Where do we start now? If you recall, on an XPS, the first thing we have to do is generate an X-ray and shine it on the surface of the sample. How do we generate an X-ray? So it all starts from here. What we do is thermionic emitter. A thermionic emitter is nothing but a tungsten or a lab 6. So or a tungsten or a lab 6, you heat that filament, and once it overcomes the work function of the element, it starts emitting electrons. Very similar to a tungsten or a lab 6 source on an SEM. Just give me a second. So just like the source what we use in an SEM, we are using a lanthanum hexaborate, lab 6. So once you heat that filament to a certain temperature, it starts emitting electrons. And these electrons are fine focused to go and hit an aluminum target. An aluminum target is nothing like a very shiny 10 rupee coin, a very small coin which is kept here. Now, As the electrons, fine focused electrons come and hit this aluminum target, it starts emitting X-rays, which are aluminum X-rays. Aluminum K alpha X-rays come out of this target. Now, one point to be noted is that as the X-rays come out of this tungsten source, not all X-rays come out with the equal energy. There is a small delta E difference between the X-rays. And for our calculation of binding energy, the energy of the X-ray is very, very important. You have to have one number, 1486 eV. How do we get that? These X-rays are made to pass through a monocrystal, a Bragg's crystal, which is arranged in such a way that the X-rays, as they enter, they get reflected internally, and as they come out with a single energy, 1486 eV. So 1486 eV K alpha X-rays come out of this monocrystal and they strike on your sample surface. They strike on your sample. And once they hit on your sample, what happens? You get photoelectrons that come from the surface. Now these photoelectrons are since it is electrons, these are negatively biased or very minorly biased. So what you do is that you use lenses. You use electrostatic lenses. You bias them accordingly, where the photoelectrons that come out, these photoelectrons are pulled towards your detectors. These photoelectrons travel through these detectors. And please remember, the whole setup that we are talking about is in ultra high vacuum, typically 10 to the power minus 9 or minus 10. So now as the photoelectrons, they all have different energy. And these photoelectrons, they go towards the hemispherical analyzer. So this hemispherical analyzer has two plates, the one at the bottom and one at the top. And these two are biased in such a way that if you recall one of the slides, we do two experiments, either a wide scan survey or a narrow scan survey. So depending upon the experiment what you select, the electrons which fall into the range, the energy range what you select, only those electrons can travel through the hemispherical analyzer and come towards the detector. And the detector collects these photoelectrons, it measures the kinetic energy, and using the software, the kinetic energy and the X-ray energy are used to find out what is the binding energy that you are getting out. So that's how an XPS basic works out. Now, along with this, you will also find there are two interesting guns which are kept. One is a flood gun, the other one is an ion gun. What is the role of these two guns in an instrument? We mentioned in one of the slides that the modern day instruments, either you have a conductor or an insulator, collecting data becomes very easy and automated. So when you have a non-conducting sample, say for example you have a glass, quartz or a wood, these are non-conducting samples. When you have these non-conducting samples, you have a charge buildup on the surface. So in order to neutralize the charge buildup, you are using a flood gun. This flood gun, usually it has both argon ions which are positive as well as electrons which are negative, which can be flushed onto the surface of your sample to neutralize the charge. So the handling of insulating samples are taken care by the flood gun. Now the other gun, ion gun, which is again uses argon ions, what is the function of it is that, if you recall, XPS is a technique which can give you information from only top 10 nanometers, super surface top 10 nanometers. If you take your sample in atmosphere, from third floor to the ground floor, you take your sample, it gets contaminated. you get carbon deposition on the surface. So all the data that collect out of your XPS will have carbon peaks which are coming out. So you need to do a surface cleaning before you actually record the data. And how do I do my surface cleaning? For such a small area, the top few nanometers, I use this argon ion gun. I use a very mild energy and I remove the contamination from the surface. And as I do all these experiments, which area I'm looking at my sample, whether my region of interest is there or not, that comes into picture with the help of all the lenses what is attached here. These lenses help you to go to your sample of interest, navigate and select your region of interest. So the next time when you go to a XPS lab, you try to identify all these important parts which are present in every single XPS, irrespective of the manufacturer who does it. Now moving forward, it comes to sample handling. When you take your sample for an XPS lab, not every sample is of the same geometry or same nature or a same shape. So depending upon your sample, you should be selecting the holder what you are going to use. For example, if you have a nice bulk sample, you can make it into small pieces. You can use this multi-specimen holder. You use a double-sided carbon tape, stick your sample, substrate sample, and in fact, you can load up to 4 samples in this quadrant. So that goes to say, at a given time, you can even load 36 samples in one go on a K alpha instrument. There might be a question, should I load a big sample? You always remember XPS is a very, very surface sensitive technique. Irrespective of how big a sample you load or how thick your sample you load, the information is only coming from the surface. So that's for a multi-specimen holder. And this is a powder sample holder. Because when you have powders, take for example, if I'm putting a powder here and here, another powder here, the moment it goes into a vacuum, as the vacuum pumps start running, you will have cross-contamination taking place and your information will be mixed up. So instead, when you have a powder sample, instead of using these kind of holders, you need to select the powder sample holder wherein it has a slot there. And on the slot, you fill in a very small quantity of your powder. Likewise, when you have fibers, there are many researchers who work on electrospun fibers. So when you work on fiber samples and when you use a double-sided carbon tape at the bottom, you will get a huge peak of carbon on your spectra. So in order to avoid that huge background of carbon, instead of using a double-sided tape, you have the fiber sample holder. So when you use the fiber sample holder, your background of carbon can be eliminated. So the information and data analysis becomes much easier. So in short, depending upon the sample what you take for an XPS lab, very carefully choose the holders what you are going to use. There are many researchers who also work on thin films, multi-layered thin films. We have a dedicated holder which is available with this K alpha as well, called the tilt module. What this tilt module does, it helps you to collect XPS data in an angle dependent way. So you can tilt your samples from 0 to 90 degrees. Why you want to tilt your sample 0 to 90 degrees? The moment you tilt your sample, the X-rays which come and hit on your sample, you are making them to go at a glancing angle. So the more and more tilt you go, the X-rays will just come at a glancing angle. You get more and more surface features instead of an X-ray just impinging perpendicularly to your sample. So if you are working on multi-layered thin films, this could be a very good holder to choose. And with the modern surge of battery material characterization requirements, there has been a growing demand where people working on battery materials, they want to protect the sample from getting exposed to atmosphere. Because the moment you expose your lithium ion material or raw material to atmosphere, the complete composition changes. So in order to protect the capability inertness of the sample, you use this vacuum transfer module. The vacuum transfer module helps you to load the sample in a glove box environment. It helps you to maintain the inertness. You pump it down and you can transfer it to your XPS system. So now using all these holders and following the right methods of sample preparation, I have kept my sample and the sample is transferred to an XPS system. This is how it looks like under an XPS system. You can choose your region of interest either to be a point, or you can draw a line, or you can choose an area from where you want to have the XPS data. It's all geometrical drawings that we do on the user interface. Now when you do it, this is how the sensitivity graph looks like. What I mean to say the sensitivity graph, this is your spot size starting from 50 micron to 400 micron. At a 400 micron, you easily get 4 million counts per second. So that's the kind of data what you get out of an XPS instrument. I'll skip this slide. It talks about the charge neutralization, which we have already spoken. So when it comes to samples, by using the right charge neutralization, still you are able to get fantastic data. Why I say fantastic data is that this is an example, a glorious example of a polyethylene terephthalate. This material has a very interesting carbon peak around the 280-285 region. It has 3 carbon peaks, and this is called the ester peaks of PET. So your instrument, if only it has a very good energy resolution, if it has a very good charge neutralization capability, the detectors are really super sensitive, that's the only way where you are able to resolve all these peaks. For generation and generation, most of these instruments were never able to resolve these ester peaks. But K alpha instrument, it was quite an easy cakewalk for us to record these PET peaks on a carbon. So now, having spoken about recording the spectra, many times it also becomes interesting to record chemical maps, because when you load your sample, very often looking at the microscope images, we are not sure what is our region of interest. So in order to select the region of interest, normally what we do is we run a chemical mapping. What this chemical mapping does it, you choose an area on your sample, you collect the spectra very quickly, and based on the chemistry, you can do a color mapping as well. Using the photoelectrons, you can do the color mapping, and depending upon the chemistry what you get, you can select your region of interest as well for analysis. Now all these techniques, what we spoke about, they are from the surface of a sample. But when it comes to a certain modern age of materials, getting data from the surface is good, but not every research problem lies only on the surface. There are instances, for example, these class of materials where surface is important, but I need to go beyond the surface. I want to understand the chemistry deep down the surface. So how do I do that? That's where you have an experiment called depth profiling. What this depth profiling does it, you have a substrate, you have multi-layers on your thin film. XPS can get you information only from the top 10 nanometers. But my interest, research problem is, I want to understand the chemistry on the surface, and I also want to understand the chemistry, how it goes down as I go down in the depth. And I also want to understand whether there is any interdiffusion of one layer from the other layer. So XPS is a fantastic technique which can help you to do the depth analysis and also measure any interdiffusion from one layer to the other layer. Now this experiment, it's not as complicated as it sounds. You can automate the K alpha, where you can give the pitch thickness of material to be removed, and you can also give how much spot size and how much material to be removed as well. And this helps you to understand the complete chemistry from the surface to the bottom in a very automated fashion. For example, here is two samples. I have a sample which also has a carbon fluorine and also carbon oxygen. So I want to understand this, and I also want to understand up to which depth this layer is filled up. So XPS is a very simple technique. It helps you to record the chemistry, remove material, and it can help you to record the chemistry of the layer which is also at the bottom. So this gives you an overall understanding of how your sample is behaving with different layers. So another example, the hard disk that we all carry day to day for data storage. It has a glass substrate, and top of the glass substrate, it has multiple layers, different conductive property, different magnetic property. It all helps us to store data. But in a semiconductor industry, understanding the layer thickness and the interdiffusion is very important. So XPS is regularly used in these cases where they understand the chemistry from the top surface to the glass substrate, and they also understand the interdiffusion across different layers. And the final example, when it comes to the glass industries, the display of glasses, particularly the large glasses, is a huge industry. It's a massive industry. And this glass industry, if they want to fine tune their glasses, what they make, it all goes with the chemistry of the thin films which are coated on the glass substrate, on top of the glass substrate. It's not a single thin film, but it is a multi-layered thin film of a precise chemistry which is layered one after another on top of the substrate. So it becomes very, very important for them to understand what chemistry is present and whether there is any interdiffusion across these layers. And for these industries, measurement under an XPS is absolutely essential. So with that, I come to the last part of my talk. I'll take the next 5 minutes to run through this, and we are done with it. So all these measurements, what we had seen until the last slide, they are XPS, X-ray photoelectron spectroscopy. So they use an X-ray source of 1486 eV. Now, they help us to get the photoelectrons from the core orbits, core shells. Now there is another additional accessory which can be attached to an XPS called as an UPS. That stands for ultraviolet photoelectron spectroscopy. So in case of an UPS, we have an ultraviolet lamp which can be attached to the instrument. So this UPS can help you to get an energy that can knock out the valence electrons out of your orbit. If you remember, the XPS can knock out the core shell electrons from your structure, atomic structure, whereas UPS is an experiment which can help you to knock out the valence electrons from the outermost shell. And this can give you information about the valence band of your sample. So if you want to understand the valence band of your sample, this UPS is a very popular attachment that is available with almost every XPS, including the K alpha installed here. So along with this XPS, you can combine the depth profiling experiment to collect multiple information in a given time. You do recording, you switch over to the UPS, record a data, do a depth profiling, come back, and this data, what we see on this slide, to manually do, it would take 8 to 10 hours. But with the automation, what is available in a K alpha, it roughly takes about 50 minutes to 1 hour to record this data. So as we approach the end of this talk, alpha, there are many other instruments, but the point to say here is XPS is a fantastic technique to learn. There are not many minds and hands who are trained on XPS. So if you get a chance to do an XPS measurement, enjoy the study, learn the instrument, and go behind the technique and theory to understand more and more about it. Because with the growth of semiconductor industry and the battery industry in India, characterization techniques are going to be hugely in demand. And when the demand goes up, the microscopy techniques like ACM, TEM, and also the spectroscopy techniques like XPS, those are the techniques the industry will look from the students. And if you have a good understanding on that, you will have a great career in analytical studies. So with that, I conclude by thanking you all for your wonderful attention, and thank you for inviting me, and it's a great honor to be here. Thank you. Is there any questions that I can address?
Good morning, sir.
Yes, ma'am.
It was a very informative session.
It's an inert gas, ma'am.
Yes, sir. Helium is also in
You can use it, also comes in helium. We are going to use it for UPS. The UPS uses a lamp, helium lamp, so we don't want to mix up the gases. The energies have to be different. And also the other point is it has to be very affordable and easy to use. And argon is obviously a great choice to have. Yeah. Yes, please.
It's a very informative and insightful
You.
one doubt. For a sample, if I'm unable to, content or moisture content, still I want to correction factors for that to get.
No, actually, there are some XPS style like ambient room temperature XPS, but those have not been very popular. But if you want to get very good data out of an XPS, your sample should not have a moisture content. There are other techniques how you can remove the water content out of your sample. There are methods which you can do, but
Let us take a by doing the drying process. Maybe because of the drying, my chemical composition may get changed.
it
So
will.
I may not get the proper.
That's been a challenge. That's an area which is yet to be covered in XPS. Because even with electron microscopy, there are methods where you can remove the water content or moisture. But what we have seen is the moment you do it, the morphology changes. It always changes. So that's been a trade-off between both ends. Fortunately, the answer is not it. We don't have a good instrument for that. What you can do is you can use a cooling stage on an XPS. You can use a cooling stage where if your sample has a water content, You can freeze your sample, use a liquid nitrogen stage, and then you can record your data. But you need to see whether that gives you the information what you're looking for. Because freezing and doing XPS is not the only objective. Whether you get the right data is also another. Please, ma'am.
Thank you for the very insightful talk. In one of the spectra, we saw some. I would like to know what that shape peak is coming from and where is.
It could be that your sample is present, you are having some contamination on the surface of your sample. Because of that contamination, you are getting a slight trigger in the shape peak.
That is.
It depends on the sample what you are using. It depends on the sample. There are ways where you can smoothen out your spectra and completely remove that peak as well. You can smoothen your spectra. But on this slide, I wanted to show the original data. That's where the originality was maintained to show that.
So it is also recorded.
Yes, yes. Yes, and that becomes particularly very important for the student community, because the moment you start smoothening your spectra so much to show a very nice data, for the referee it becomes very easy to pick out that you are doing all tricks. So it's always better to stick with the original data and report it as it is. Thank you. Contamination removal, material removal for depth profiling.
How we can find.
So when you record a spectra, usually you get some unexpected peaks, which are not very uniform. It comes randomly as you go across from one region of your sample to the another region of your sample. The moment you do a quick 30-second cleaning or even a 45-second cleaning, then you will find that gets eliminated very evenly. So these are the contamination which might have picked up from the atmosphere or wrong sample handling. Because many a times we have seen students, they come for an XPS measurement holding the samples with their bare hands. So when you bring a sample with your bare hands, there is no point in doing XPS. You will get the chemistry of your fingerprint, not the sample. So it all goes with the sample handling and preparation. Yes, please, sir. Yes, sir. Very nice question, sir. In fact, we have our engineer there. Yes.
What is the
Sir, I didn't get the second part. What is the difference between? Intensity. Uh, yes, sir. Sir, yes. Uh, sir, yeah, thanks for asking that, sir. Sir, whenever we plot an XPS spectrum, the X and Y scale, the X scale you have the energy range, the binding energy range, and on the Y scale you have the intensity scale. So the intensity scale refers to the number of photoelectrons that the spectrometer has collected for that particular energy range. So depending upon the number of photoelectrons, you get the intensity peak, which can be high or low. That's how the intensity versus energy range is done. And in terms of calibrating the spectrometer, normally we have a standard set of 5 to 6 samples. And the very popular sample that we do for calibration is the silver sample. So on a AG3D 5 by 2, that's one popular peak, we align the spectrometer and we check for the intensity. A silver peak at a 3D 5 by 2. That's one calibration sample we use. And for the insulating samples, we normally use the polyethylene terephthalate, PET. And for the spot size calibration, we have a different sample as well. So there are set of 5 to 6 samples which help us to calibrate starting from the spectrometer up to the ion argon energy gun. There are different calibration methods. And if you'd like, once you come for the demo, we have our engineer who can very quickly show you how we calibrate those. Sorry, sir, can you? We, sir, we do multiple fittings we do. Yes, absolutely, absolutely.
And you get the straight line, and you imagine what is the intercept.
Absolutely, yes.
Then that the intercept, that is the work function. And that is work function means the correction factor. I want to actually that is.
Agreed, sir, totally agree. Yeah, thank you. Thanks for bringing this, sir.
So Karthik sir, one more question on online.
Absolutely, sir.
Particularly on samples with redox.
Sir, I may not be able to comment on the redox particular sample nature, but we do have a dedicated holder which is called work function module holder. So this work function module holder comes in with 4-point biasing. So with the 4-point biasing, you have two internal bias which comes from the instrument, and the other two biasing can be done externally by the user. So with this 4-point biasing, you can do a work function module measurements for your sample. And for that redox, I may not have the knowledge to answer that, sir, because I have not worked on that. Yes, please, sir.
No, now we have a demo. Speaker, thank you for accepting our invitation.
Thank you, sir.
And giving a nice lecture on XPS. Thank you, sir. Yes. Sir, you can.
Thank you very much.
Wow. Okay, thank you.
Thank you very
Thank
much,
you,
sir.
Thank you.
Thank you, sir.
And participants now, there is one small physical exercise. Let us, and we are dividing our batch 66 onwards, batch 2. Batch A will be going for GSI,